Okay, so in this video we are going to look at banking of roads wherever there is a bend in the road. So what is happening is, just consider a situation that you are driving your car and you're driving in a straight line, and if suppose there's a turn in the road here and you want to go around this bend. So this is a circular path. This is a circular path, which means that your car or you are traveling in a circular path here. Now we know that the circular path is not possible without centripetal force, circular motion. This is a really important statement, just like I talked in the last video. Circular motion, I'll repeat it here, circular motion is not possible without centripetal force. So this car here is going around this bend. You need some centripetal force. Who is providing this centripetal force? The car is going around the bend. I mean, you're driving and you know that car is going around the bend. So there must be some agency which is providing this centripetal force. If you want, you can pause the video and think about it. If not, then I'll give you a hint. Suppose you're driving in icy condition. The road is all ice. There's ice on the road, and you're driving, and now you're trying to turn on this road, and you will find that it's difficult to turn, and most probably if you're driving at a faster speed, you will not be able to make the turn and you will go straight. And why is it so? Obviously your answer would be that because there is no friction on the road. Now with this thinking, we can conclude that when a car is going around the bend, the centripetal force is provided by the friction between the tires and the road. So I can write it here. When a car going around a bend, the required centripetal force is provided by the friction between road and tires. And if, just as it happened in the case of icy roads, if the friction provided is not enough, then you don't have enough centripetal force, which means you will not be able to make the round. Yeah, so it's a situation, and sometimes, let me clean this thing up here. Sometimes to avoid this possibility, when your road is not able to provide you enough friction because of various conditions, maybe because of ice or because of water, the roads are banked. Banked means roads are tilted by a certain angle, by a small angle, so that when you're going, you go round the bend comfortably. If you have seen bicycle tracks and velodromes where they have bicycle races and all those things, you must have seen that the bicycle tracks are normally banked. It's the same concept here, and we are going to look at how the banking helps a car go around the bend in a safe manner. So I will clean this thing up, or maybe I'll keep this thing here and I'll go from here. So suppose my car is going like this. All right. So I'll bank the road, and here I will draw the banking of the road. So this is the horizontal road. I mean, I haven't come out really well. This is the horizontal road, and then it is banked by a small angle theta here. So if you look from here, it's a cross section kind of thing. You're seeing this is my car. Doesn't look like a car, but it's a car. And these are the car's wheels. I mean, we are looking from the back. We are outside and we're looking the back of the car, and we see that there's a car is there, and we got two wheels here. Now this road has been banked. So Okay, so before I talk about something called normal force, let me talk about what a normal force is. So suppose you have, I'll come back to this in a moment. Suppose I have, suppose this is my table, and a book is lying on, a box is lying on this table. The box mass is 2 kilogram. So this box has got few forces acting on it. One force is the mass of the weight of the book, weight of the box, which is m times g, that weight is there. But this weight is not unbalanced, because if this box was acted upon by this force, the box would be moving. But we know that the box is in a stationary condition. Box is not moving at all. It means all the forces must balance out. So we got this force here. It means there should be an exact and opposite force acting in this direction. And this force is known as the normal force. And who's providing this force here? This force on the box is applied by the table here. So this box, again, just to repeat, got two forces acting on it. One is the weight acting downward, and that force is cancelled by the normal force, which is applied by the table. Normal force means perpendicular force. So basically, normal force is always perpendicular to the surface which is applying the force. Okay, let's come back to my car here. So this car is on this surface here. So it has a normal force acting here. We can call it Fn. And now you will see that this Fn has a, if you draw from here, that angle will be same as this angle. This angle is theta, and that angle will also be theta. Just to see how it is theta, you can see that, for example, your road is horizontal first, and this is your car. Now you tilt the road, the whole thing you rotate by theta degree, so it goes like that, and that goes like that. Maybe I'm not making much sense here. So this is suppose this is the box here, and this is plane surface, and this is my normal force here now. Now if I rotate the whole thing, by theta, so this will become theta, the box will come here, and that normal will also move by theta, so that angle will be theta, and that's why this angle here is theta and this angle is theta. Let me clean this box and draw a bigger picture, because I will be drawing different forces on it. Let me draw it again a bit bigger. So that's my banking, that's my car, and on the car this is the force, normal force, and just as discussed last time, in the previous figure here, this angle also be theta. So the road has been banked by an angle of theta. This theta is known as the banking angle. But I'll clean this up because I need to draw forces here, so I'll clean that up. Keep in mind that this theta is the banking angle, and this is my normal force. It is perpendicular to this surface here. It's normal to this surface. That's why we'll call it normal force. Now this normal force, now we can see that it has two components. It has one component in horizontal direction and one component in that direction. We know that this component will be Fn cos theta, and that will be Fn sin theta. Now at a glance, this should tell us why the banking helps. When we bank the road, what is happening is that we have a F normal force which has a component in the horizontal direction, and this component in the horizontal direction is providing the centripetal force. Just recall that the road is traveling in this manner, and we have banked the road like this. So you need centripetal force in this direction. This Fn cos theta is there, and it provides the required centripetal force for helping the car go around the bend. Now we can find the value of this theta with the speed and all those things. So first let's look at this car here. It has got Fn cos theta acting on it. It got Fn sin theta acting in this direction, and it has one more force acting in this direction, and that is the mass, that's the weight of the car, which is mg. M is the mass of the car and g is the gravitational acceleration. Now this car is not moving in vertical direction. I mean, if this car is not moving in this direction, it means that the forces in the vertical direction should cancel out. All right, so vertical direction, we got Fn cos theta here going up and mg going down. So we have Fn cos theta is equals to mg. Now our car is going around the band with a speed of v. So what's the centripetal force needed for the car to go around the band? So centripetal force is centripetal force required for the car to go around this band is equals to m v square over r, where r is the radius of my circular path and v is the velocity. All right, now in the situation where this component of Fn, this Fn sin theta, provides all of this centripetal force, I will not have to depend on the friction between tires and the road, and this is known as the optimum banking angle. And in this situation where all our centripetal force comes from this, we can write the equation Fn sin theta is equals to our total required centripetal force. We got the two equations here. From this equation, I'll go back, just go here, I can rewrite that as Fn is equals to mg cos theta, and here and I will substitute this value in Fn here in this equation. So in place of Fn, I'll write that mg cos theta times sin theta is equals to mv square over r, and m and m will cancel out here. So, or maybe let's write it like this. I want to keep theta here, so I want to get rid of mg from here, which means I will divide by mg here and divide by mg here on both the sides. So I'm left with sin theta over cos theta is equals to mv square over m rg. This m will cancel out as well, and this thing become tan theta. So I have equation on left hand side, we got tan theta, and on the right hand side I got v square equals to rg. This is a really important equation. It gives us the optimum banking angle. So what it gives us, that if your tan theta is equals to v square or rg, we do not depend on friction, or in other words, friction is not, friction means I'm talking about friction between the tires and the road. Friction is not needed to go around this band. Yeah, and this is where I'm going to stop, and we'll continue this discussion in the next video. We'll look at some problems as well.